Welcome to Lecture 2, Part 2 for Nuclear Forensics. This is the second part of the lecture on radiochemistry in nuclear forensics. This lecture continues the discussion of the role of radiochemistry in nuclear forensics. And in the second part, spin, parity, and its relationship to decay are discussed, along with nuclear reactions. The electron and neutrino spin can be aligned or anti-aligned during decay. So if they're aligned, if they're parallel, the spins will sum up. The spin change will be on the order of 1, either +1 or -1. If they're anti-parallel, they cancel, the spin change will be 0. So there's two possible alignments for creative spins. One is Fermi, where the spin change is 0. These are dominant at low A isotopes, and Gamow-Teller, where the spin change is 1. And these tend to be observed at higher A. If we examine low A isotopes, the number of protons is approximately equal to the number of neutrons. So if I swap a neutron to a proton state or a proton to a neutron state in the shell model, which we'll describe later, the occupied states are going to be about the same. The overall spin change will be 0. This isn't true for Gamow-Teller, where as I go higher in A, I tend to have more neutrons than protons. So if I take a neutron and convert it to a proton state, that spin change will be non-zero and it tend to be on the order of 1. Sources can have a mixture of Fermi and Gamow-Teller spins. These spin types can be used to define the decays. Now, for even nuclei, let's say mirror nuclei, where the number of neutrons equal the number of protons.
Neutrons and protons can be in the same shell.
I can get transitions from 0+ to 0+ decay. That can take place by a Fermi transition. These heavy nucleons, Gamow-Teller is the main mode, as we already discussed in the previous slide, because we need to account for the spin difference. Now, these nuclei can be rather complex, where the rate of decay depends upon the overlap of the wave functions of the ground state of the parent and the ground state of the daughter. So what's the probability from the ground state of the parent to a state in the daughter? And this final state depends upon the decay mode. So spin and parity changes from parent to daughter, and the overall delta of the change, this degree of the change, is going to have an effect on the rate of decay, or as we see, the decay constants. So I can get half-life information from this. I can also use the half-life information to understand nuclear states. I can calculate the decay constant if the wave functions are known. So an initial observed rate indicates the quantum mechanical overlap of the initial and final states of the wave functions. And we'll get into this in more detail when we discuss Fermi's golden rule, where Fermi came up with an equation to describe the decay constant based upon these initial and final wave functions and their overlaps. We can use this information to develop something called comparative half-lives. This is based upon the probability of an electron energy emission coupled with the spectrum and Coulomb correction. And we're going to call this Ft, or F0 T1 half. This is basically a comparative half-life for a transition, where decay constant is equal to log 2 divided by 1/2 is equal to K, our matrix element, and this F term. Our K term, well, that's a mixture of a number of constants and a Fermi term. And this F0 state is an integration of all the energy states that are possible for this decay. This assumes that the matrix element is independent of energy, because we're not changing it as this energy changes, which is true for allowed transitions, not necessarily true for forbidden transitions. So we can look at this Ft, or F0 T1 half. It's a comparative half-life, and this could be thought as a half-life corrected for differences in Z, right, which accounts for a Coulomb behavior, and W, which is the total kinetic energy. There's a rapid way for estimating Ft and energy. Then we'll show this equation fundamentally, the log ft is equal to log f plus log t1 half. T1 half needs to be in seconds. There's ways of calculating these log f values. We showed an integration on the previous slide. Here we're going to have three equations that are listed here for beta minus, positron, and electron capture, where all these equations are going to be our functions of the Q value, then the daughter Z. So this is fairly straightforward. If I know my daughter Z and I know my Q value, I can determine the log F value. If I get the half-life in seconds, well, the log Ft is nothing more than the log F plus the log of the half-life in seconds. By doing this, we can get a range of log Ft values that basically break decays into allowed transitions, first forbidden, second forbidden, third forbidden. I put two tables here that you'll find in the different textbooks that describe the ranges for the forbidden transitions, or the allowed and the forbidden transitions. And what we generally see is that for a given type of transition, there will be a value for a spin change and a parity change. So for instance, a first forbidden will tend to have a spin change depending upon if it's Fermi or Gamow-Teller of 1 or 2, along with the parity change. Second forbidden, 2 or 3, no parity change. Third forbidden, 3 or 4 with the parity change, etc. Now we can use these equations to calculate some log Ft values. And let's go for the positron decay of oxygen 14 to nitrogen 14. The Q value for this reaction is 1.8 MeV, and the half-life is 70.6 seconds. So if I take my positron equation here, and now I plug in my values for the decay of oxygen 14, so the Z is now the Z of nitrogen. It's the daughter. The Q value is for the E. I come up with a value of log F beta plus of 1.83. T is 70.6 seconds. Log of that is 1.84. I get a log FT value of 3.767. And that fits into a super allowed category, or over here, a super allowed between an allowed category. So from this transition, we would see that this decay is a fairly allowed decay. We can perform another log FT calculation. Now let's use the beta decay of bismuth 212. The Q value is listed here. We need the Q value in MeV, so it's 2.254 MeV. The half-life is 3,600 seconds. Well, we actually need to get the beta decay half-life, which winds up being 5,625 seconds. Remember that this is a 46% beta branch, so we use one of the equations that we discussed earlier. If I use my equation for the log F beta minus, I have this equation. I plug in my half-life. I plug in my Q value. I get my log F is 3.37. My log T is 3.75. I get a log FT value of about 7.5. And I actually compare this to what's listed in the table of the isotopes. As you see here, these values here are my log FT values for the individual transitions. So this bismuth 212 going from a 1 minus state to a 0 plus state has a log FT of 7.3 listed here. We calculated to 7.5. That's a pretty good estimation. And we will see that this is a first forbidden type transition based upon the value. So what drives these changes in these log FT values? Let's examine it for mercury 205. Here are these log FT values. what we see is that the decay in beta is really driven by the change of the spin and parity from the parent state to the daughter state. The lowest log FT value is for a 1/2 minus to 1/2 plus state. And we see that these transitions, if we were to try to go from a 1/2 minus to a 5/2 plus state, we have the highest log FT value, and that's driven by this overall change in spin. We could go from this 1/2 minus to this 1/2 plus state. However, the energy transition is not the greatest. If we could have the same spin and parity, often the decay will be favored for the larger energy transition. Similar to what we described with alpha decay, and particularly with beta decay, there are selection rules for gamma decay. These selection rules can be based upon electromagnetic forces. Since the photon radiation arises from electromagnetic effects, it can be thought of as a change in the charge and current distribution in the nucleus. And if we think about charges and currents, we can talk about these distributions in terms of electric moments, if the charge distribution, or if there's a change in current, that can be thought of as a magnetic moment. So we can describe gamma decay as either magnetic, if it has to do, if it's yielding from change in currents, or electronic, if it's change in charge. And we're going to go over some rules that talk about spin and parity related transitions and how that can be used to classify whether decay is magnetic or electric, M or E. We're also going to discuss the polarity as it relates to magnetic and electric distributions of gamma decay. So monopole, quadrupole, etc. One of the things we are going to see is that the transition probabilities decrease rapidly with increasing angular momentum. So changes that occur, if they have large spin and parity changes, the probability is going to decrease, just as we've seen with beta decay. And if we go to the table of the isotopes, we'll actually see that the transitions, such as the one listed here in E2, is shown for the certain gamma transitions for the decay. So for instance, here's this decay state that we looked at before. For europium 152, and we can see the energies of the transitions and their classification of an E2 transition. And we'll just explain that in a little bit more detail in the upcoming slides. So we can describe the angular momentum from the gamma decay being the L of 1, 2, 3, 4, etc. as a pole. So an L of 1 would be a dipole, quadrupole, 2 to the 2 is 4, octapole, etc. Shorthand notation for electric or magnetic 2 to the L pole is written as E1, or excuse me, EL or ML. So for instance, an E2 we'll call an electric quadrupole. And those are shown over here. We have an E1 is electric dipole, and M1 is magnetic dipole. E2 is an electric quadrupole, M2 magnetic quadrupole, etc. Now there's routes where we can determine the multipole of the decay. And all we're going to do is look at the spin and parity of the initial and the final state. So here we have the spin and parity of the initial state and the spin and parity of the final state. And we can use this to determine the angular momentum of the decay, which will be used to evaluate what this polarity is. So basically, the polarity can run from the sum and the difference of the initial and final state. If the initial and final state have the same parity, the allowed transitions are even L electric multipoles and odd L magnetic multipoles. And if the initial and final states of this gamma transition are in different parities, the electric multipoles are of odd L and the magnetic multipoles are of even L. So let's go through an example, or two examples, that demonstrates this. Let's assume that there's a gamma transition from an excited state of 4 plus to a ground state of 2 plus. So if we go back over here, the angular momentum will run from the sum and the difference of these values. So 4 plus 2 is 6, 4 minus 2 is 2. So L will be between 2 and 6, so it'll be 2, 3, 4, 5, and 6. The parities are the same. So we go here, initial and final states have the same same parity. Magnetic multipoles will be even. Electric multipoles will be even. Magnetic multipoles will be odd. So if we go from 2 to 6, magnetic multipoles are even. So 2 will be an E, E2, M3, E4, M5, E6. Those are the allowed transitions, and generally speaking, the lowest multiple transition will be observed. So one would expect to see an E2, so an electric quadrupole transition observed. And we can see here the electric quadrupole will have a spin change of 2, which is what we predict, and no parity change. So we can actually get this out of the table. So again here's another table where we have an electric quadrupole, spin change 2, no parity change. Now we can look at another example, cesium-137. We can pull this out of the table of the isotopes. The cesium-137, the gamma decay, it goes from the 11/2 state to 11/2 minus to the 3/2 plus. So 11/2 plus 3/2 is 7. 11/2 minus 3/2 is 4. The states are of different parity. So the electric multipoles will be odd L and the magnetic multipoles will be even L. It goes through 4, so the magnetic, so it'll be M4, E5, M6, E7. And as we saw, M4 is the lowest, and that's the value that's listed right here on the table of the isotopes.
Based upon the review and what you've known from previous classes, you should be able to discuss a decay scheme, such as this is decay of isotopes of aluminum and neon and even sodium to magnesium. We see that there's beta decay routes to different states. There's positron decay routes shown here, and these transition probabilities are listed along with their log FT values. And this should be able to interpret, you should be able to interpret this for understanding the spin state of ground and excited states. Here's an example of another decay scheme which you should be able to interpret. This is for americium-242. It shows the ground state, which is a half-life of 16 hours, and the excited state, which is a half-life of 141 years. Little unusual that the transitions between the half-lives from the ground state is shorter than the excited state. The transition from the 5/2 minus to the 1/2 minus is related to this long metastable state. And then the other aspects of the decay scheme, which are shown here, are the decays from this excited state to the Neptunium-238, so an alpha decay, or decay from this ground state to curium-242, which is a beta decay. There's also the decay to the americium-242 to the plutonium-242, which also represents a beta decay, but an electron capture or positron decay, most likely for this isotope an electron capture. Another example of decay scheme, which you should be able to interpret, is shown here for the decay of americium-241. Americium-241 is known to have the photon, the gamma decay, at around 60 keV, shown here. The yield for this transition is around 36%. So 36% of the time this photon is observed. One can look at the data from the decay of americium-241, the 5/2 state, the ground state of the neptunium-237 daughters, 5/2 plus. That's a parity shift. There's the higher probabilities actually from the 5/2 state to this 5/2 state, which has an 85.5% transition. That is the 59.6 or 59.5 keV. That's the high transition, which is shown here, that this photon decays around 36% of the time. So the remainder of the transition must be photonless. But you can also see the transition values for this alpha decay. This has the as far as the hindrance factor, closest to 1, so it's the least hindered transition. Other background information you should be familiar with is nuclear reactions. One can start off with a fundamental nuclear reaction, an alpha particle on nitrogen, yielding this reaction. This, by the way, was the first transmutation reaction that was observed, where the alpha particle is just coming from alpha decay. The shorthand for this reaction is listed here, where you have a nitrogen-14 target, the particles, an alpha proton comes out, and we're left with the resulting isotope, in this case oxygen-17. One could also talk about the stages of a nuclear reaction, as far as the types of reactions that can occur. One is an independent particle, the compound nucleus, and the outgoing reaction. So as shown here is a schematic. One can have the independent particle coming in, interacting with the target nucleus in a number of different transitions, peripheral collisions, total fusion, a grazing collision where some nucleons can shift, and then some sort of scattering. All these reactions can occur with different cross sections, different probabilities, and that's what the next section that we'll cover is related to cross sections and how it relates to probability of a reaction. The cross section is used in equations to calculate reaction rates. You can think of the cross section as the probability of a reaction
to occur,
and it's a term that we've already discussed.
The cross section symbol is sigma, and some values for reactions with neutrons can be found in the chart of the nuclides.
For example, this tellurium-130, there's cross sections that go from thermal neutron, resonance neutron, to the metastable state, and then thermal resonance to the ground state. These values are described within the chart of the nuclides. So it's a term we've already discussed, and it has a dimensioned area. It's 10 to the minus 24 centimeters squared is the value for the cross section, which is called a barn. And barn value is strange unit, right? 10 to the minus 24 centimeters squared. Well, a nuclear radius is around 10 to the minus 14 meters squared. If I took the area pi r squared, I'd get a dimension that would be on the order of 10 to the minus 24 centimeters squared. Now, this value originates from the probability of a reaction between a nucleus and a particle, and it's proportional to the physical cross-section of the area presented by the nucleus. This isn't completely true. For instance, with a charged particle, you have a Coulomb barrier to overcome. With slow neutrons, you have resonances that are based upon some quantum mechanical properties. Basically, a general trend would be that the reaction cross-section is going to be fundamentally proportional to the area that the particle can see from the nucleus. And this is really true. If you have fast particles, the cross-section is never greater than twice the geometric cross-section of the nucleus. Cross-sections for fast particles tend to be close to a barn. It also depends upon the exact reaction that you're looking at. And what we're going to see when we explore cross-sections is that we'll have some cross-sections which are close to a barn, seem reasonable, and then some cross-sections that are multiple barns, thousands of barns. So in essence, it's as if the nucleus expands. That's not what's really happening. Quantum mechanics comes into play, and you have wave function overlaps that increase the probability of reactions. So let's see how cross-section can be used in some reactions. The cross-sections that are in the chart of the nuclides are for neutron reactions, and the sigma that represents the cross-section will have a symbol next to it, a gamma or a F, gamma for just neutron capture, F for fission. We'll explain this in more detail when we discuss those different reactions. But there's also cross-sections for accelerator reactions. So in an accelerator reaction, a beam of particles strikes a thin target with a minimum beam attenuation. So the energy loss as the beam travels through the target can be neglected for this equation to be valid. And that's important because
for accelerator-based reactions, the cross-section is a function of the projectile energy. For a given reaction, the change in cross-section with energy is called an excitation function, and we will discuss this in more detail later in the course.
So we have these terms where we have the incident particles per unit time, a beam current. We have the number of
target atoms
per centimeter cubed. We have a target thickness in centimeters, so we see that we get an inverse centimeter unit here. And then we have the cross section, which is in centimeters squared. So we see that the area values get removed. For reactors, we use a different equation, and we assume that a particle,
in this case the neutron, has
a uniform flux, is impinging upon a target and cross section
for a given reaction with the target isotope.
So we've got the rate of reactions, some sort of processes just over here, how many reactions are occurring per unit time, is equal to the cross section times the number of nuclei that are in the sample times the flux. So that's particles per centimeter squared per second. And this is a property, this flux is a property of the reactor. This target, that's the property of the target that you're putting in. And this is the cross section that one can find. Of course, if I had an unknown and I measured the rate of the reaction, the rate of the process, and I knew something about the reactor flux, and I knew the number of atoms that were in the target, I could figure out the cross section. And if I had an unknown reactor and I wanted to measure its flux, I would put a target that's known in with a cross section that's understood, measure
the reaction rate,
and I could evaluate the flux. So these equations provide us an opportunity to evaluate terms and processes in nuclear reactions. Those equations that I showed in the previous slide are fundamentally correct. However, we are neglecting an important consideration, and that's the decay of any isotopes that are produced while the production is ongoing. And we need to consider something a saturation factor.
In the previous slide, we discussed rates of formation. Another way of evaluating these rates of formation is shown here using this equation, where if the activity of an isotope is measured after the reactions to produce that isotope, and that activity is divided by this saturation factor, 1 minus e to the minus lambda t, that'll provide the rate of formation. And that should be the same rate of formation value as calculated from the equations on the previous slide. Since the measured activity divided by the saturation factor yields the isotope formation rate, one could evaluate cross-sections, fluxes, and target information using experimental data from an irradiation, as we discussed in the previous slide.
But let's think about what this saturation factor means. As one is producing an isotope, when it's made, it also has a probability of decaying.
If the isotope is stable, this probability is 0. Otherwise, it is based on the half-life.
So if you're producing an isotope that has a half-life of 100 years, and you're producing it in a reactor, and that reaction takes an hour, the probability that one of the atoms you made that has a half-life of 100 years decaying within that hour is pretty small. So we don't really need to include the saturation factor. However, if you're irradiating a sample for an hour and the half-life of the isotope that you're producing is 3 hours, a measurable amount of that isotope may have decayed. And you need to include this saturation factor. Using the saturation factor, the number of product atoms produced is equal to the number of target atoms times the cross-section times the flux, as we discussed on the previous page, divided by the decay constant for the atom produced times the saturation factor, 1 minus e to the minus lambda t, where lambda is the decay constant for the isotope produced. If the number of product atoms are known, the activity can be found by multiplying the number of product atoms by the decay constant. And all we need to do is rearrange this equation. The activity of 1 is equal to the initial amount of target times the cross-section times the flux, same equation as we used in the previous page, multiplied by 1 minus e to the minus lambda 1t. So this is the decay constant of the isotope that you're producing. This term, 1 minus e to the minus lambda t, is called the saturation factor, and it gives you an idea of where you're going to reach a maximum level. As one continues to irradiate, and if I look at the amount of half-lives of the daughter, and I compare that to the irradiation time, I reach a level where longer irradiations does not produce more material. This is because over here, as let's say within one half-life, it's fairly linear. Some of the atoms that have been produced have decayed because the atoms are being produced over this entire half-life time. So the ones that were initially produced at the very beginning of the reaction have a 50% probability of decaying, while those at the end have a very small probability of decaying. But as I increase this, more of the initial atoms have a probability of decaying because they're experiencing many half-lives. And you just reach a point around 7 half-lives where fundamentally reached an equilibrium, that you're producing more from a reaction, but you're losing those atoms that were made earlier. So this tells you that if you're doing a production reaction, you should never go more than 7 half-lives of your isotope. So if I was making an isotope that was an hour, anything more than 7 half-lives is not worth it. In fact, you can make an argument that, well, the amount that I gain from 4 to 7 is pretty small. 3 to 7 is pretty small. From 2 to 7, I'm only gaining 25% more. So one could evaluate that. Is it really worth that extra time to produce a relatively small amount of material? So we have these saturation factors, and as a function of half-life, you can see what sort of percentage of the saturation you're reaching. Let's compare these two equations in two different scenarios. One where the irradiation time is short compared to the half-life, and one where the irradiation time is long compared to the half-life. So for our first example, let's use a reaction to make iron 59, this isotope, 44.5 day half-life, from iron 58. We'll add a neutron to the iron 58. It will absorb that neutron, give off a gamma, and make iron 59. It gives off the gamma because it makes an excited iron 59 state. That photon makes it decay to the ground state. So it's just a simple transition, and we see that as this N comma gamma iron 59. So target, projectile, reaction product, reaction product. Another way of writing it is shown here. We'll go over more detail about this reaction later in the course, how we this sort of nomenclature. But we can also write it as iron 58 plus a neutron goes to a photon plus iron 59. The cross section we can get right from the chart of the nuclides. It's 1.3. I write it here 1.3 times 10 to the minus 24 centimeters squared, because remember it's in Barnes, so this is in Barnes, and 10 to the minus 24 centimeters squared is our Barnes unit. So let's take our equation that we have here. We want to get N, right? We want to get the number of atoms that are sitting in the target. I state that there's 1 gram of iron. The molecular weight of iron is listed here. We use Avogadro's number. So now we've got the number of atoms of iron. And then I'm going to use this value because this is for iron. I didn't say any sort of enriched iron. I just said regular iron. And 0.282% of iron is iron 58. So I need to normalize it by that. And I get the number of targets as 3.04 times 10 to the 19th atoms. All right. So we've got our information. We've got our flux, which I provide here, a neutron flux. We've got the number of atoms, and we've got the cross section. So let's plug this information in to the equation. Flux, number of target atoms, cross sections. I get a rate of 3.95 times 10 to the 8th atoms per second. I say I want this irradiation for an hour. So there's 3,600 seconds in an hour. So from this, I get 1.4 times 10 to the 12th atoms of iron 59 are made in 1 hour. Now this reaction does not include the decay of any iron 59 that's during that hour of production. Let's include that by using the saturation factor. So the same terms that we used in this equation, we got to add something about the decay, so we got to bring in the decay constant. I provided the decay constant here, but it's just log 2 divided by the half-life, but this is all in seconds, so make sure if you were to do that yourself, you would convert days into seconds. So we use this equation. Let's plug in the terms. The number of iron 59 atoms that are made is equal to the number of target atoms times the cross section times the flux divided by the decay constant times 1 minus e to the decay constant times the time. That's where our time, that's the only place where the time really comes in. And this is basically providing a saturation factor. It says what percentage of the material is available. And what we get is a value that's shown here. We get 1.4 times 10 to the 12th atoms. We got 1.4 times 10 to the 12th atoms. And it says, you see, you need to go down to the 4th significant digit in order to see a difference. And as we would expect, this value would be less than this value. So this shows that you could use either equation if something is relatively long-lived. If you have a spreadsheet that's set up and you're inputting the data, it doesn't really matter which equation you use. They would both equally well describe the reactions. All right, let's consider a condition where the radiation is relatively long compared to the half-life. So let's take the formation of manganese 56 from manganese 55. Again, a neutron capture reaction. So manganese 55 captures a neutron, gives off a gamma, makes this manganese 56. The half-life of the manganese 56 is 2.6 hours. We'll do an hour irradiation. So when we say that the radiation is long compared to the half-life, doesn't necessarily need to be longer than the half-life. It just needs to be a good fraction of the half-life in order for the saturation to come into play. All right, so let's get some of the data. Our cross-section for the manganese 55. So remember, the manganese 55 is absorbing the neutrons, so you need that cross-section, not the manganese 56 cross-section. We have our cross-section is 3.3 times 10 to the minus 24 centimeters squared. It's 13.3 times 10 to the minus 24 centimeters squared. The 13.3 Barnes value is listed here. Again, this is for thermal neutrons. You can assume I'm using a thermal neutron flux. This is for epithermal neutron flux or resonance energies, resonance neutron flux. If it's unclear in a question, you're free to use whichever one you want. I will try to specify for instance, radiation from thermal neutrons. We have our data, right? We need to get the number of manganese targets. Said there's a gram of manganese. All of manganese is iron 55. The molecular weight of that manganese is manganese 55. The molecular weight of that manganese 55 is listed here. So we have a way of calculating the number of manganese targets from 1 gram. That's sitting in the neutron flux. Let's use our equation. Let's input the terms. The rate is equal to the flux times the cross-section times the number of targets. We get a rate of 1.45 times 10 to the 12th atoms per second, 3,600 seconds in an hour. We get a value that we should make 5.24 times, or 5.25 times 10 to the 15th atoms of manganese 56 in an hour. Now remember, this equation does not count for decay. Let's consider decay. We use this equation where we have the saturation factor along with the decay constant. Let's plug those values in and let's solve. We get a distinctly different value. We get 4.6 times 10 to the 15th atoms. So this is a demonstration that if you are producing an isotope that's relatively short-lived, where the irradiation time is long compared to the half-life, you need to definitely include the saturation factor for accurate assessment of the amount of atoms that would be produced. We introduced this equation a few slides ago, where we can determine the formation rate based upon a measured activity and this saturation factor. So let's look at the example from the manganese 56 that we provided in the previous slide. We've gone through how we determine this value. Our activity, if I know the number of atoms of manganese 56, the decay constant, right? So activity equals lambda n. I have that value. I get so many becquerels, so 3.4 times 10 to the 11th becquerels. That's my activity. I substitute the activity into 1 minus e to the minus lambda times the time, and I get a production rate. So this production rate includes it's the overall production rate, and it does include the decay as a function of the irradiation time.
Equations that show the production of isotopes from accelerators were also provided, and we're going to show an example of that using the production of astatine-211 based upon conditions that are used at the University of Washington. The equation that was used is shown here, and the components of this equation, as a reminder, include your beam current, which ultimately is particles per second, so it's the projectile particles hitting the target, and then target information, which includes the atom density, so atoms per centimeter cubed, times the target thickness, that'll get centimeters squared, and then we get the cross-section, which is shown here from experimental data, and this cross-section for this reaction is about 1,000 millibarns, so that's 1 barn, and we'll use that as the cross-section. And remember, that's in 10 to the minus 24 centimeters squared per barn. So the data that we need to accumulate to run this equation is the same if we go for the equation that does not have the saturation or the equation which does have the saturation. The only addition for the saturation equation is the inclusion of the decay constant. And again, just like the reactor example that we showed on the previous page, if we know the activity and divide that by the saturation factor, we will get the production rate. So for the production of astatine-211, which is used as a radiopharmaceutical, the reaction includes a bismuth target, a helium projectile, 2 neutrons come off, and the product nuclei astatine-211 is produced. The helium target is a monovalent helium beam, And at 30 MeV, it has a beam current of 70 microamps for this accelerator. The unit ampere is used to convert the microamps to charges per second using the conversion that 1 ampere is equal to 6.24 times 10 to the 18th charges per second. And since the helium projectile is monovalent, 1 helium projectile is 1 charge. So from the 70 microamps, you multiply that by 6.42 times 10 to the 18th charges per second per amp, and you get 4.37 times 10 to the 14th particles impinging on the target per second. For the number of atoms per centimeter cubed, the target is metallic bismuth. Assuming 100% density of your target, use the density of bismuth, which is shown here to 9.7 grams per centimeter cubed. Convert that to atoms using the atomic mass of bismuth and Avogadro's number. You get 2.808 times 10 to the 22nd bismuth atoms per centimeter cubed. So that's the number of targets per centimeter cubed. The target thickness for this example will be 0.1 centimeter. So that's the value for X. For these calculations, the target information may be provided directly. For example, as opposed to providing the thickness and the density, one may be provided the number of atoms in the target or the mass of the target that is being bombarded. And the cross-section, again shown here, has a value of 1 barn. 1 barn is 1 times 10 to the minus 24 centimeter squared. Continuing with the example of the production of astatine-211 based upon the conditions used at the University of Washington, the decay constant for the astatine-211 isotope needs to be determined. The data from the chart of the nuclides show that the half-life is 7.21 hours for astatine-211. Converting that into the decay constant is simply log 2 divided by the half-life. Remember that the half-life should be converted into seconds, so it's 7.21 hours with 3,600 seconds per hour. You get a decay constant of 2.67 times 10 to the minus 5 inverse seconds. For this example, calculate the production of astatine-211 atoms for a 3-hour irradiation. Again, 3 hours, convert that into seconds. 10,800 seconds, set that as time t. So for the two examples, let's do the production. For no decay correction, the atoms of astatine-211 is equal to the equation we've shown before. And since it's a production rate that is not decay corrected, we'll just multiply it by the number of seconds for the irradiation. And we're going to set that equal to N1 as a comparison point. N1 is equal to particles per second times the atom density times the target thickness times the cross-section times the time. And those values are shown here with the particles per second, atom density, target thickness, cross-section from the previous slide, and the irradiation time provided above. One gets the production of 1.3 times 10 to the 16th atoms of astatine-211, and that's equal to 3.5 times 10 to the 11th becquerel, and that's simply found from activity equals lambda n. Comparison to the decay corrected equation, which is shown here, substituting the terms and the addition of the decay constant. The equation terms are shown here using, again, the same terms as the non-saturated equation with the addition of the decay constant and the saturation term. One gets the production of 1.2 times 10 to the 6th atoms of astatine with an activity of 3 times 10 to the 11th becquerels. And we see that the decay correction shows that the amount of astatine produced is reduced since the irradiation is for 3 hours. The half-life of the astatine is 7.2 hours. They're on the same order. This is a demonstration that Both equations can be used. However, the decay correction equation certainly is the suitable equation for this condition based upon the half-life of the produced isotope.
Let's continue evaluating these energetics in reactions and discuss the Q value. The Q value is not necessarily equal to the energy that's necessary for the reaction to occur. Oftentimes, a reaction to proceed forward will need to overcome and be greater than the Q value. And this is because products will also have kinetic energy that need to come from the reaction. The Q value, as we'll see, is a center of mass reaction, and we need to convert this to the laboratory frame. This is due to the fact that there's conservation of momentum. The particle kinetics energy must be retained as products kinetic energy. So in other words, all the energy of the system that's defined by the Q value is not necessarily available just for the reaction. Some has to go into moving the resulting products. And the amount that's retained as kinetic energy of product is based upon the projectile mass. The retained kinetic energy becomes smaller as the target increases with the equation that's listed here, where if I take the Q value and multiply it by the fraction of the mass of the projectile divided by the mass of the projectile plus the mass of the target, I'll get something called the equation for the kinetic energy that's necessary for the equation. We'll see this is going to eventually come into something called the threshold energy. Now let's look at this and think about what does this mean for a reaction where I have something where I'm making a compound nucleus. Let's make this a relatively straightforward reaction. Curium plus oxygen 18 going to rutherfordium 266. What does this mean if I either accelerate oxygen into a curium target or curium into an oxygen target? Well, if I accelerate the curium into an oxygen target, I use the curium as a projectile, this value, this kinetic energy, is about equal to the Q value. So we see because it's equal to 248 divided by the sum of 248 plus 18. Now if we go the other route, which is actually done experimentally, where we accelerate oxygen into curium, we wind up with only the kinetic energy being a smaller fraction of the Q value. This is one reason why you often accelerate the light particle into the heavier target. Now we can use the equations we just discussed to correctly evaluate what energies are used for a reaction to occur in the laboratory. And what we need to do, we need to consider both a laboratory and center of mass frame. For the laboratory frame, we need to consider the conservation of momentum. So in a laboratory, here's an example of a target. A projectile hits the target. We get our product and the other product from the reaction. Both the two products are moving the particle that impinged upon the target. The target we can basically stay stationary. The particle moves and we have two other bodies that are moving. So we need to consider the fact that the products are moving after the reaction. They're moving at a certain energy, a certain velocity, and at a certain angle from the initial trajectory of the projectile. Now there's an equation here where we see that the Q value can be a sum of terms related to masses and the kinetic energy. So the kinetic energy of X would be the particle here. The kinetic energy of P is our projectile, and we also have information related to the kinetic energy of the product. And this allows us to consider evaluate the reaction if we know product information such as the angle in which one of the products come out of the reaction and its energy. We can find the Q value if that angle and the kinetic energy of X are measured and particles known. So if I look at this equation up here,
I see that I have certain terms where the Q value is a function of different kinetic energies. This equation here relates these kinetic energies to values that could be measured, masses, and something that's known from the experiment, such as the initial kinetic energy of the particle. So if one can measure the angle and the particle kinetic energy, one can find the Q value of the reaction. Now for center of mass, where we often do equations, the total particle angular momentum is 0. In this case, it's as if the products and the reactants are hitting each other, and we get a center of mass frame that looks as shown here. We can talk about the kinetic energy from the center of mass and evaluate the two equations where we relate the kinetic energy of the center of mass and the kinetic energy of the lab, and it just winds up being equal to the kinetic energy of the center of mass is equal to the lab times a ratio of the mass of the particle and the sum of the mass of the particle and the mass of the target. The equations we just evaluated can be used to determine a threshold energy for a reaction, so the minimum energy that's necessary for the reaction to occur. We have this relationship where the Q value plus the kinetic energy of the lab minus the kinetic energy of the center of mass has to be greater than or equal to 0. We can solve for terms related to the relationship between the center of mass, the kinetic energy, and the laboratory kinetic energy. So we substitute the kinetic energy of the center of mass for the laboratory kinetic energy times the ratio of the mass of the particle divided by the sum of the particle and target. We come up with the rearranged equation, which is listed here. We've put the Q value onto the other side of the equation. We take the kinetic energy of the lab term out. Now we can rearrange this equation and solve for what the kinetic energy of the laboratory must be greater than. We get to this equation here. We rearrange. We substitute the mass for A, which is a good reasonable substitution. And we come up with this very simplified equation where this threshold energy, this minimum energy for the reaction, has to be equal to the opposite of the Q value times the mass of the projectile plus mass of the target divided by the target mass. So you can use this to evaluate should we use a heavier target or a heavier projectile. And as we discussed earlier, by inspection we could see that we prefer to use a heavier target if possible. Using what we've just discussed, we can evaluate the threshold energy for this Rutherford reaction. Our reactions listed here. Let's take our terms, put it into our threshold energy. Our Q values listed here, projectile, target. This equation is transformed. The terms are listed here, and we get 1.5 MeV for the threshold energy. Now this is just the minimum energy for the reaction to occur, and it doesn't account for the Coulomb barrier. The Coulomb barrier is the charge interaction that we need to overcome to get the two particles right next to each other. The Coulomb barrier comes from the fact that I've got to take these charged particles and contact them. So the equation for the Coulomb barrier is listed here is a function of the charges, and this is our term describing the charges, divided by the radii. If we use this equation for the radii, where nuclear radii can be approximated with a constant times a to the 1/3, we can substitute this equation and show a Coulomb barrier, which is just a relationship of a constant, the z of the projectile, z of target, the a of the projectile, the a of the target. This term for since this term for the Coulomb barrier is based upon R naught, you may see some variations in this equation. This equation that's listed here that we're substituting and going to put into our terms is used for an R naught of 1.5 femtometers. So we can take this term, put in our terms, the terms coming from our Rutherford reaction, where we get the Z's and the A's, and we see that the Coulomb barrier is equal to 3.36 MeV. This is a center of mass equation, and we need to convert this into a laboratory frame, so we multiply the terms by the ratio of the target projectile divided by the target, and we see that what's needed in the laboratory is a alpha particle with an energy of about 4.3 MeV needed for this reaction to occur, which is what Rutherford was able to see.
As an overview, the reactions that we've discussed often have energies which allow particles to be emitted from the nucleus, and if we can emit particles from the nucleus, we change those isotopes. We can relate this to cross sections. Then we have an understanding of the possibilities of production of certain isotopes based upon the nuclear reactions. So one can look at, in this case, neutron energies. So you could talk about a probable neutron energy, your average neutron energy, and then the probability of having a neutron in a certain energy range. The cross section, for example, with a neutron reaction, is going to vary based upon the energy. So if we have a range of energies, we'll have a range of possibilities for the production of certain isotopes. If we talk about a certain energy which happens to be dominant, for instance, if we talk about the average neutron energy range versus the most probable neutron energy range, the types of reactions that can occur at these different energies varies. So if we have a reaction in which the neutron energy varies from one condition to another, we'll get different isotopes that are manifest and get some information about the energetics of the reaction. Right, this concludes part 2 of lecture 2 for nuclear forensics. The information that we discussed in this part, we talked about the beta decay and other decay modes, we related spin and parity with decay, and we talked about nuclear reactions. Please proceed to part 3 on the fission process.